This is a proof that you can't reach row 5 in a game of Conway Checkers. It follows on from a main video on the Numberphile channel, so you probably should have watched that first. If you've landed here and haven't seen that video, I'll include links on the screen and down in the video description.
Actually, we can start on the board, and as a matter of fact, I don't even need the line, it's distracting for now. So at first, what I'm going to do is try to create a feature that doesn't change, a so-called invariant. If you have seen before Pebbling the Chessboard, a previous video on Numberphile, you would know what I'm talking about. So if you want, you can stop, look at it, and then come back. However, if you are up for the challenge, let's just do it right away. Here are two checkers. I want some feature not to move. So what happens is, this checker is going to jump over and then this one will disappear. In other words, I have two old checkers and one new. So whatever is happening for the old checkers should be happening for the new one, if that feature is supposed to be an invariant, not to change. Now, a very common way of creating invariants, just like in Pebbling the Chessboard, is to put certain numbers in each cell of the board. And those numbers are not random. They are powers of something. In Pebbling the Chessboard, it was powers of 1/2. But here we are in a much more complex situation. Powers of what mysterious number do we have to put? So we need to do a little bit of a calculation here. So let's do it. So here we go. We have 3 squares next to each other, and we are trying to put powers of some mysterious number x. All right. So I will put x to the power n. The next power, x to the power n plus 1, and x to the power n plus 2. So they will be adjacent powers of x. The old guys are those two, x to the n and x to the n plus 1. And the new one is x to the n plus 2. So what we will do is add up the old numbers and try to get the new one. Is this possible? X to the n plus x to the n plus 1 equals to x to the n plus 2. Well, there are too many x's, so if I want to solve for x, I should divide by the smallest power of x. So for instance, if this were x cubed plus x to the 4th equals to x to the 5th, we should simply divide everything by x cubed to get rid of the extra fluffy stuff here. So x cubed divided by x cubed is 1. We have 1 extra x if I divide x to the 4th by x cubed, and 2 extra x's on the right hand side. Well, this equation starts looking extremely familiar, because if I put the lower terms on the other side, push them over, I will end up with one of the most famous equations in the history of mathematics. A simple quadratic equation, which is nevertheless famous. Why is it famous? Do you know, Brady?
Because it was in the movie?
Well, it definitely has been in Da Vinci's Code, that's right.
There you go.
What's that number that was in that movie?
Golden ratio.
Golden ratio all over again. It keeps popping up everywhere in this world. Let's see, is it indeed a solution to this equation? Now, if you have had very good algebra course in high school, you would know the quadratic formula. Ax squared plus bx plus c equals to 0. The two roots of this quadratic equation are minus b plus minus square root b squared minus 4ac over 2a. Let's try. So in our situation, x1 and 2 will be, I'm putting the fraction bar, b here is -1, so negative 1 is just 1. plus minus square root -1 squared minus 4. A is here, and that's 1. And C is -1. And all has to be divided by 2. All right, this is not so hard. We end up with 1 plus or minus 1 plus 4 is 5, so square root of 5. And bingo, we end up with 2 possibilities. One of them is 1 plus square root of 5 over 2, which is known as the golden ratio, and it is denoted by the Greek letter phi. And if you wonder about how large this number is, it's approximately 1.6. And this golden ratio truly appears in very unexpected places. But we have another candidate here. The other one, x2, is 1 minus square root of 5 over 2. And this is obviously negative. It's approximately negative 0.6. It's kind of a twin to the golden ratio, but it's the evil one. I'll just call it the evil twin.
Evil twin?
Yes,
right.
yes. Let's just do that.
Okay.
It's the evil twin of the golden ratio. And if you actually want a notation for it, you can say that it is bar of the golden ratio. Now, could one of those two numbers that came up so naturally from this game be the mysterious x that we will use to place in every single cell? The answer is no. Unfortunately, we're not yet there. Why not?
Well, didn't you assumed 3, 4, and 5 at one point?
That's a good question. Actually, the same equation quadratic will come up no matter what you have upstairs, because all you have to divide is by the smallest power. So if we take this approach, we will always come up with those two solutions. The reason that none of them works is a very prosaic, pedestrian reason. It just is not going to do what we want. For instance, imagine now we're on an infinite chessboard, not just on 3 adjacent cells. So if I use the golden ratio, I will have something that looks like this. 1 in one cell, 1.6 or approximately 1.6, 1.6 squared, 1.6 cubed, and this will keep going and going and going. On this side, I'm going to have probably the negative powers, so 1.6 to the minus 1, 1.6 to the minus 2, and so on. Okay, now what happens if I add up all of those? What number would I get? Well, 1 plus something that's bigger than 1 plus something that's bigger than 1 plus something that's even bigger than that. Keep on adding and adding, and you will end up with infinity. So we have a problem. I don't want infinity to enter my computations. I'm trying to show that something finite, like reaching the 5th row, is impossible. I don't want that infinity. Why did we get infinity? Because the golden ratio was too big for our purposes. The golden ratio is bigger than 1. And that is no-no. Okay, well, maybe.
But, you can't just decide what you want, though. Isn't mathematics, don't you have to just accept what mathematics serves up to you?
I will define what I like if it does what I want. And it's a free country. I can put whatever I like in those cells. I see that the golden ratio is not going to do what I want. So it's not the number for us. It looked very promising, but it's too big. Now, if we try the evil twin is relatively small. It is negative 0.6. And if I feed it into a similar argument, I can actually come up with a finite number. But the problem with this evil twin is that it's negative. And remember, we wanted a feature that moves only in one direction. But what do powers of negative numbers do? They flip-flop. So for instance, negative 0.6 is negative. And if we raise it to the power of 2, negative 0.6 squared, that negative is going to disappear. And so you will end up with something positive. And this will keep flip-flopping between positive and negative numbers. And so eventually we're not going to get our nice monovariant, this feature that either only increases or only decreases. So we are out of luck here using those two numbers. But there is something that is close to them, something intermediate that satisfies an almost similar equation that's going to work. What could it be? It's not the golden ratio, it's not the evil twin, it is that reciprocal of the golden ratio. Because the golden ratio was too big. If I take its reciprocal, that will be less than 1 and it will still be positive. The thing is that people actually know about the golden ratio and they don't know about this other number. It's like sitting in the background, ready to jump out at any moment, and there you go. And you will see that it's somehow connected to our helper, the number that we're looking for. Okay.
But if you were just like making it, if you're just like inverting it now and saying, I'm going to use 1 over because it suits me better, why don't you just use a half? Or, 0.3? Like, why don't you just use any old number? Like, if you're just playing fast and loose now and just saying, I'm not happy with that number, I'm going to make it smaller, how can I make it smaller? You could just use any old number.
It's a very reasonable suggestion, extremely reasonable, but guess what? First of all, I have to oblige to the rules of the game. So somehow I have to stay close to that equation that we obtained. Don't stray too far from it. Secondly, we actually did see the powers of that mysterious number already. Here they are. 1.6 to the negative 1 that we wrote earlier. That's a negative power of the golden ratio, but it's a positive power of its reciprocal. And 1.6 to the negative 2 is also a positive power of the reciprocal. So actually, half of what we wrote before is exactly what we need. And I am going to replace the other half, the larger half that had the golden ratio, by a symmetrical array of numbers, so that everything actually is smaller than 1.
Okay.
But I want to make a point. So strictly speaking, you don't need to do this calculation. But it will link probably what you have done in high school to what we're doing now. So I will try to derive a formula for the reciprocal of the golden ratio. All right, so 1 over phi is 1 over, what was the golden ratio? 1 plus square root of 5, yes?
5 or 2?
Oh, I wrote 2, look at me. So it is square root of 5. Okay. So this 2 goes on top. This is what I was thinking about. 1 plus square root of 5. And so when you see such nasty things in the denominator, you want to rationalize them. So you multiply top and bottom by something called the conjugate of them. It's almost the same, but with a negative sign. Okay, so what is this doing? I will have in the numerator what I have, 2 times 1 minus square root of 5, but the denominator will become nice. There is a formula here at play, a minus b times a plus b, and that turns out to be a squared minus b squared. Let me write this down for you. A plus b, a minus b is a squared minus b squared. So by this formula, you will have 1 squared minus square root of 5 squared. So at the end of the day, we are getting to a simplification. 1 minus 5, which is minus 4 in the denominator, a little bit of cancellation, minus 2, and then we flip the sign on top, square root of 5 minus 1 over 2. So this is our reciprocal of the golden ratio, and if you compute it, it will be close to 0.6. Does this number remind you of something?
Yeah,
have we seen it before?
Yeah, so,
It's the evil twin, except we have taken out the minus. In fact, that's not a coincidence at all. This mysterious number is indeed the negative of the evil twin. So it is both the reciprocal of one of the solutions and the negative of the other. And for homework, you can actually try to prove that. I don't need to do it. But now we have a pretty good idea of what this number is. So I think we are ready to populate our table with powers of this very, very useful reciprocal. I'm going to call it x once again because this is what we concentrate on. So remember we had this infinite board, all right? And I'm just ignoring the line wherever it is. This argument is going to work. You need to start with 1, so put your checker anywhere you'd like, and we will, in that cell, write 1. Next to this 1, I will put powers of x, powers of my mysterious number. So we start populating the table with powers of x, but not only it will be horizontally symmetric, but also vertically, because we also have vertical moves. Whatever we do horizontally, we should duplicate it vertically. And so there you go. The pattern is emerging. Brady, what should I put here?
is that going to be what, like x to the 2? Or?
Yep, that's right. That would be x squared. This will be x squared, x squared, x squared. But how about here?
I'm going to put x squared there as well.
You're absolutely right. Because the adjacent powers of x are sitting in adjacent cells. But that forces us to put right here x squared, x squared, x squared. And now look at this. We have a larger square, kind of diamond shape turned, with x squares. And we keep on going. So if we go back to the board, this is what it's going to look like. Here my x squared. And let's just do one more, x cubed, and I think the viewer will know what is going on. So we will have x cubed, x cubed. I'm moving along the diagonal because I know I will need those adjacent cells filled with x cubed. So what is this thing good for? Did we achieve our goal to find a monovariant feature? We need a little bit of work to see what is going on. So imagine you have checkers placed right here in positions x and x squared. And you are moving towards 1, you're jumping like this, and then you are freeing this cell. Okay. So our original sum, x plus x squared, did it change? So we had x squared plus x occupied, but after the move, only 1 is occupied. Did this sum change? What do you think? We are replacing two small numbers. All of those powers of x's are actually small numbers because they are powers of 0.6. The sum of two smaller numbers by 1, this has the hope of actually being equal to 1.
What, when x equals 0.6?
Yes, but where is this coming from? It is coming from our original equation for the golden ratio. So that original equation said that 1 plus x is equal to x squared. But then we reciprocated x, right? So what equation is the reciprocal satisfying? All right, so here is what we will do, a little bit of magic. Put a question mark here. We don't know if this is true, but I know that x is the reciprocal of the golden ratio. So I'm going to substitute the golden ratio squared plus, again, the golden ratio, it's reciprocal, is this equal to 1? Let's simplify. 1 over phi squared plus 1 over phi, is that equal to 1? Let's clear the denominators, multiply everything by phi squared. So what do we get? Here I will get 1. Here I will be having only 1 phi, and on the other side, phi squared. But that's exactly our equation from before. 1 plus the golden ratio is the golden ratio squared. So actually this is correct, and then everything before that is correct. All right, so let us start summarizing. Indeed, if I have checkers placed like this, and I am moving towards 1, the sum is preserved by what we showed. How about if I had the checkers here and I'm moving towards 1? Will the sum be preserved? Yes, because this equation is simply multiplied by another x. So let me just write this. I will have x cubed plus x squared. Is that x? Certainly, because I just multiplied this equation by x. Okay. But Brady, what happens if I go vertically? Would that also work?
Same.
That's right, because we made it symmetric. So, if you move towards 1, your sum is preserved. It's an invariant. There is one move, though, that is very special. What if you jump over 1? I think the sum will decrease, because originally you had x plus 1, but then you replaced it just by x. So the sum decreased. Oops. So it's not going to be an invariant, but it might be a decreasing monovariant. So now we put all of our hopes into showing that what we've constructed is actually a decreasing monovariant. So let me backtrack a bit. So
yes, what's a decreasing monovariant is just something where the number can never go up.
Exactly.
What's wrong with the number going up?
Well, then it's not going to be a monovariant.
But neither is the decreasing one. That's not a monovariant either.
The process is a lot more controllable. If you start from 5 and end up going to 1, you know that you have traversed this interval only going down without exiting it and doing 5, 7, 3, jumping up and down and doing something randomly. So if you have a function, just a general function or a feature, you don't want it to go up and down. That's very hard to imagine, very hard to control, very hard to predict. But if you know that that feature can never go up, then you have a pretty good idea of what's going on. In fact, you may need only finitely many steps to reach a level where you need to go. So, backtracking, what's happening in the real game is you have some random checkers, who knows where on this board. So you will sum up the numbers of the occupied cells, and it is this number that we hope to be decreasing monovariant. There is one other type of moves, though. What happens if you go away from 1, like this? Did the sum increase or decrease? If I had originally put my checkers on x and x squared, and then I replaced this by x cubed, let us plug for x 0.6. That's a good approximation. So I will have 0.6 plus 0.6 squared is being replaced by 0.6 cubed. Well, which one is larger? Definitely the left-hand side, because it contains larger numbers than this very small one.
So it's decreasing.
Yes,
it
is decreasing. Let's draw one's row here and one's column. If you move towards one's column like this, no matter where on this grid you are, your feature, your sum, will be preserved. It won't change. However, if you move away, it will decrease. It will go down. The only non-trivial move is if you go over the row or column of 1, you will decrease by 1, but that's still decreasing. So after all of this work, we actually got our decreasing feature, the sum of all of the occupied cells. All right, so let's go back now to the original problem. How do we show that something is impossible? We may have seen similar arguments before on other Numberphile videos, but basically, instead of trying to provide some arguments for why it cannot happen, you slow down and say, okay, well, suppose it is possible. Let's see what will go wrong. In other words, we are arguing by contradiction. So let's say Brady tells me, yes, I can reach row 5. And then I will ask Brady, all right, so here is my dividing line. You will place your checkers underneath and play. I don't care about this right now, but you show me where is the cell, the first cell on row 5 that you will reach. Just point to me.
Okay, well, 1, 2, 3, 4. That one there.
Okay, so I'm going to place a checker there. So that's the checker that Brady reaches, the first one in row 5. Well, that's not possible. Why? Does Brady have enough soldiers, enough checkers underneath the line to actually reach there? Even if Brady put checkers all under the line everywhere,
millions and billions,
infinitely many, okay, infinitely many checkers, does he have enough fuel to reach the top? So imagine this is all filled with checkers.
infinite, all right.
So if I manage to add up what is on this half of the board, I will get some number, right? Let's say I end up with 5, okay? Is 5 good? Because what do I have here? So I didn't tell you where to put the original 1. I'm going to put the original 1 exactly where Brady claims he has reached row 5. So that's 1 right here. That's 1. This is where Brady has reached row 5. And then populate the rest of the table with those powers of x, right? So let's say I added up then everything underneath the line. These are lots of numbers. And I ended up with 5. I don't see a problem because this sum can either stay the same or decrease, but all I am trying to reach is 1. So it's okay, well, that sum somehow decreased and got to 1. But is the sum 5? Actually, it turns out that if you add up all of those numbers underneath the line, you're going to get only 1. Let's see why this is so. We need another sheet.
All right.
Okay, so here is the line, and we have how many cells up? We have 5. And here is our 1. This is the cell that Brady said he can reach. Okay, underneath we have x, x squared, x cubed, x to the 4th. And what we're really interested in is what is happening underneath the line. So I'm going to write just a couple of powers here in this central column. X to the 5th, x to the 6th. And here we have x to the 6th, here we have x to the 6th, and you can keep extending. Okay, so now what we need to do at first is calculate what's happening only on one row. And so for that, I'm just going to go to the easiest row that has 1 and use its result later. So we have x, x squared in this direction, and x, x squared in this direction, right? Okay, so let us start adding just for this row. we will have 1 plus x squared plus x cubed and so on and so forth. Well, does this remind us of something? This is so-called geometric series, and probably it's a topic that you will study in second semester calculus. And such a geometric series actually has a very nice formula when you add it up. The formula is 1 over 1 minus x. X is the ratio here. So in other words, every time you move to the next term, you are multiplying by this x every time. Okay, now this works only if x is small. How small? Between -1 and 1. Luckily for us, our x is approximately 0.6, so we can add up. Now, however, this 1 over 1 minus x, I don't like it. This ratio, because it's just very complicated. Is there a way to simplify it? Yes, because we have a very helpful equation before. X squared plus x is equal to 1. And so from here, if I pull the x to the other side, I have x squared plus x equals to 1. Here we are pulling x to the other side. We will get more or less what we need. Here is your 1 minus x. I'm going to go up here and substitute instead of it x squared. But the story gets even better. Remember that this x was the reciprocal of the golden ratio. So golden ratio is going to come back into our story. So what happens if I divide 1 by x squared? It will turn out to be the golden ratio squared because you've reciprocated. So to summarize, half of this row is the golden ratio squared. How about the other half? We just can't forget that. So let's add. So the other half is x plus x squared plus x cubed and so on, right? Now, I don't really need to repeat this whole calculation here.
So we haven't got the 1 anymore.
No, we don't. Yeah. So what do we have to do? Just subtract 1 from our previous answer because we are missing it here. So this whole thing is our previous answer minus 1. Okay, this is all very nice, but now we should add them up to get the whole row. All right? So row with 1 adds up to phi squared plus phi squared minus 1. Now this is pretty complicated. Where did we get the golden ratio? There was another equation for the golden ratio from before. And it is this equation. It looks like the previous one, but it's different. And here when I put phi squared, I end up with phi squared minus phi minus 1 equals to 0. So phi squared minus 1 is, put the phi to the other side, is just phi. Okay, so we are getting somewhere. It's not yet exactly what I want, but it looks like this expression being replaced by phi, this is what I have. Can I also do something with this? Yes, I can. It's exactly the same equation. Okay, so look at this. So phi squared plus phi, this is some algebraic gymnastics that I'm going to produce, is factor out phi plus 1. What is phi plus 1? Phi plus 1 is phi squared. So there are lots of relationships about the golden ratio that you can extrapolate just from this single quadratic equation. So when you substitute this here, I have phi squared. So what did I get, Brady? Phi cubed. Done. That was the hardest calculation.
Okay.
So if you are really determined to find how much we have just in row 1, this is phi cubed. This is the golden ratio cubed. Okay, well, let's just start writing here in a different pen. So row 1 adds up to phi cubed. What does row 2 add up to? Now, I'm not going to redo the whole calculation. It's not necessary. But watch this. Every number on the first row is being multiplied by x to get it to the second row underneath. So the sum that we got before must also be multiplied by x. But what was x? X, our mysterious number, was the reciprocal of the golden ratio. So what happens if I multiply phi cubed by 1 over phi? Let's see. Phi cubed times 1 over phi is phi squared. Oh, things look promising. How about the next row if I add up? What do you, Brady, think?
Well, you must knock another one off the power, so it must drop to 5.
Exactly, because we keep multiplying by the reciprocal of the golden ratio. But how about here? That's an interesting row.
What do we do? What does it do? Does it drop to 1?
5, that's right. 5 times the reciprocal of it is 1. Keep on going. Now we drop to the negative powers of phi. And finally, we come to the region where we were interested in the first place. This is underneath the line. So the first row underneath the line must add up to phi to the negative 2. So we need another picture. So we just concluded that if I add up everything on the first row below the line, I will get phi to the negative 2, and then we keep on going. Phi to the negative 3, phi to the negative 4, and so on and so forth. Now we need to add up all of those in order to see what's going on with our army of checkers that we can put here. For the whole region underneath the line, our answer starts like this. You keep adding powers, negative powers of the golden ratio. Now, this is just way too complicated. Let me factor the first one. And what will be left? 1 plus phi to the minus 1 plus phi to the minus 2 plus etc. etc. But guess what? We just computed this a while ago. This is 1 plus x. Remember, x was the reciprocal of the golden ratio, plus x squared, and so on and so forth. Let's see, where was that? That was phi squared. So this sum here overall is phi squared. So what is everything under that line? It is phi to the negative 2 times phi squared. Well, that's just 1. All this computation to get 1 for adding up these infinitely many numbers underneath our line. Going back to our chessboard. Here is the line, and all of the cells have been somehow populated for the sake of the experiment. And we've added all of the numbers underneath the line, and we got 1. Can we, actually I'm going to move the line because I need one more row on top. There you go. Is it possible for Brady to reach row 5?
Oh, it feels like it is possible now.
Yeah.
Just possible.
Just possible.
Yeah, because as long as I don't vary, I can stay on 1.
You can, so you need to stay on 1.
So I can just get there.
Just get there, barely, really. So tell me, after you play all of this, so you start with an army that adds up to 1, you stay constant, you land on your cell, how many checkers do you end up with?
1.
Just 1. Can you have more? Like for example here?
No, it must be the last move. It must be the final thing I do.
Well, that's not the reason though. Because if you had more than one of those checkers, you have a 1 here. Remember, the 1 was on this spot. Plus something more, your sum will have increased. Starting from 1, you ended up with something more than 1.
No, because my that's my second to last move. And that, so as long as that adds up to 1,
Yes.
and then that adds up to 1, I'm all right.
So actually you're proving my point. All I wanted to say is that at the end of this game, there can be only 1 checker left. Any extra checker means that the sum is more than 1, but we can't increase. So Brady plays with his army of checkers, and at the end of the game, in order to reach this place, he has only this checker left. Well, Brady, how many moves did you make to decrease your infinite army of checkers to 1? How many moves was that?
An infinite number.
Infinite number, because every move reduces the number of checkers by 1. So if you play finitely many moves, you will reduce this infinity by finitely many checkers. You'll still have infinitely many. So there is no way to fit this bigger carpet in a smaller room. No matter what you do, it's going to pop up in one corner. If you need all of those infinitely many checkers. Now, do you see why? Because if I have even 1 removed, I will start with a sum that is less than 1. Well, I can't get it to 1. So I need all of the checkers.
But so if I start with an infinite number of checkers, I can get to 5. I'm just always on the way there.
You're always on the way there. But if you tell me I reached row 5, then it means the game stopped and you've done it. And you've done maybe 1 billion moves, but that's finitely many. So it is impossible, actually, to reach row 5.
Well, I used to say, and I'm still inclined to say occasionally, that I hate it, that I hate the game of life. I don't really, at least I don't anymore.
How about we test our skills on finding just the sum of the first row?